Okay, so welcome, and today we're going to start applications of integration, so physical applications. So we're going to talk about things like density, mass, hydrostatic pressure. What else can we talk about? Probability. We can talk about that too. So all of these things involve integration, and so we're going to start with density. So let's talk about developing a function or an integral for density here. So we're going to use the example of a rod, a thin rod or wire. And this has a lot of engineering applications as well. So let's say we have a rod, and the rod is, we oriented the rod on the x-axis. Okay, so we can develop this. And we're also going to assume that the rod is thin enough that we're going to treat this as a two-dimensional object. So we're talking about a very thin rod. Okay, and we're also, if we look at the interval from A to B as the length of the rod, then we can find mass by first, using density as rho, so constant density. We're going to assume for a moment constant density. If the density is constant in the rod, then which we're going to use rho here, then it's just mass divided by length, right? It's the mass per unit length, right? Now, if I wanted to find the mass of a rod that has a constant density, then that's easy. That's just an algebra problem. So I just take the length of the rod times the constant density rho, and I have my mass, and I'm done. But that doesn't, we don't always have uniform density. Okay? What if the density is not uniform? So what if the density changes as you move through the pipe or the rod, right? That's more complicated, but that's also more realistic. Okay? Can't always assume that we have a constant density in our materials. So, what do we do then? Well, then we're going to have to use a density function that a function of distance, right? A function of distance through the rod. Okay? So the density function, which we'll call rho sub x, right? And so what we're going to do is we're going to take this interval, right, of the length of the rod, and we're going to subdivide it into n subintervals. Okay, you guys know where I'm going. So we're going to do this again, and we're going to partition this into regular intervals. And what we're going to do is we're going to pick a sample point, x sub I star, and we're going to plug this into our density function. Right? Now, what is the mass of this subinterval? Well, we're going to use the same sort of formula here for mass. So we're going to call this m sub I. So the mass of the ith subinterval of the rod. And so we're going to say this is equal to what? It's going to be the length of the rod, that partition. So it's going to be x sub I minus x sub I minus 1 times the density of that subinterval. Okay. Now, the thing is as you know, and you probably already had me on this, is that, well, what's this distance? This is just delta x, right? Regular subintervals. So this is just going to become rho of x sub I star times delta x. And that's for one piece. And of course, now let's set up our sum. So we have n subintervals, right? So let's do it for each one. So, and then to get the whole mass of the rod, we're going to add them up, right? So let's do that. And we're going to form another Riemann sum here. So the mass of the rod is approximately equal to the sum of all of the masses that we calculated throughout the rod from A to B. So we're going to take the sum of I from I equals 1 to n of rho of x sub I star delta x. And if we take the limit, right? If we take the limit as n approaches infinity, of this sum, we get the integral that we're looking for. So it's going to be from A to B, the integral from A to B of the density function, rho of x dx. So in this case, it really just comes down to the density function. So we're going to integrate the density function from A to B, and that will give us the mass. Okay, next we'll go through the theorem.